Hi everyone, welcome back. In this section we're going to look at some applications of double integrals to areas of science, statistics, probability, and also mathematics itself. In particular, we're going to look at some applications to physics, so the idea of center of mass, moment of inertia. We're also going to look at applications to mathematics itself, this idea of computing a volume of a solid of revolution, and we'll see how it relates to double integrals. And we'll finish up with, in the second video, we'll finish up with a application to statistics and probability. Now, we're only taking a brief look at applications to other areas of science, but the idea is that this brief look should give you some insight into how these things can be used in other fields. In fact, the applications are very widespread, so we're only going to be able to take a brief look at further applications. So let's get right into it. The first thing we want to do is we want to look at the mass of a lamina. So a lamina is just a really thin plate. It can be of various shapes and various densities across that shape. So here we've got this sort of lima bean blue shaped lamina. We're looking at it down from a top-down view. And the idea is it's made of a material that's of varying density. Now the density in this case, because we are looking at a two-dimensional object here. We're thinking about a very thin plate, so basically a two-dimensional plate. This density is mass per unit area. So we've got this function that tells us what the density is. Now, once we know density, if it was a uniform density, we would just multiply by the area and we would get the total mass of the object. But since it's varying in density, we can't just multiply density times area because the density changes over the surface of the lamina. So what do? Well, we attack it like we would any other problem in calculus. We chop it up into a bunch of little bits, and on each little bit we approximate it by a constant. So we approximate the density over that little bit by just a constant at some sample point. So there's our picture. We've split up our lamina into a bunch of little squares or little rectangles. They don't have to be squares, but little rectangles. On each rectangle we pick a sample point. That's that xij, yij stars. And on that at that sample point we evaluate the density. And so I can find the density of that little orange region. And then what do? Well, we look at what is the mass of a small rectangular region. So what is the mass of that small rectangular region? Well, it'll be the density of that region. So we'll call it Mij for the math of the ith-jth region there. So it would be the density of that region, and we're using a sample point in that region. So if we evaluate the density function there, we assume we've cut this region up into such small, tiny little bits that we can assume that the density is constant across that little tiny piece I've just cut out. If you worry that, okay, well then we're not getting the exact value, that's fine. But what we are going to do is take the limit as these size of these rectangles go to 0, and that gets us to our exact value. So for right now we chop it up into little bits. The density of the ith-jth little bit is that row of xij star, yij star. We multiply it by the area of the little bit, which would be our delta x, delta y. That gives us the mass of that tiny little rectangle, and then we would sum over all of them. So the total mass we get by summing over all of these rectangles. So we'll go from I equals 0 to m, j equals 0 to n to get over all those rectangles. We sum over the mass of those ones, and then we look at the limit. The number of these rectangles go to infinity, or in other words, the width and the height of them goes to 0, and that gives us our total mass. So in other words, our total mass is the limit as m and n go to infinity of these sums. I equals 0 to m, j equals 0 to m. What is Mij? That's rho xij star yij star times delta x delta y. And that is precisely our definition of the double integral as a limit of a Riemann sum. So this is precisely the integral over that region R of the density function dx dy. So that means if we integrate the density function over the entire region, what we get is the mass, and that's what's stated in the box above. Now, this is a common theme that gets done throughout calculus and applications of calculus. The idea is, if we think sort of big picture, what we've done here, we said we've got this function that represents density, and it varies across the entire lamina. So what we do is we chop it up into little bits and imagine that the density function is a constant across that little bit, and then work out the mass of the little bits and sum them all up. But we do this across a continuum, so this turns into an integral. And so the way it's best to look at this is the following. We look at this expression here, and we say, what is that? Well, that's the density at a point times dA. So this is our mass element. Right? Just like this is our area element. dA is our area element. Area of a little small, tiny infinitesimal sized piece. And so multiplying by the density at a point on that piece gives us our mass element. And then we sum over all of these, but there's a continuum of them. So we're not summing over them, we're integrating over them. So integrating the mass elements gives us the total mass. So that's how we can get our mass of our lamina. Now what can we do with that? Well, that can get us to our next concept, which is the center of mass. So now we've got this lamina, or this plate, and what we can do is we can ask for, where's the balancing point? Where can I sort of put something right underneath it under a single point and have it balance perfectly? And that's what this picture is showing. There's this x bar, y bar point, so those are the coordinates of the point, where we can perfectly balance this lamina on that point. How do we find those coordinates, x bar and y bar? They're given by these expressions. X bar, or the x center of mass, is given by 1 over m, so 1 over the mass, times the integral of x times the density function over the region. One thing to keep in mind here is that it looks like we just have to evaluate one integral to find x bar, but we don't, because m is given by the integral above, the one we just talked about on the very first slide. So this is that integral above. And so what that means is that x bar is actually the ratio of two integrals, the integral of x times the density function over just the integral of the density function. Now also in this formula is the integral of x times the density function. This has a name. This is known as the moment about the y-axis. And we denote it by capital M sub y. So that's the double integral over the region of x rho xy dA. So that's the moment about the x-axis. So what that is really doing is it's saying, okay, I've got this lamina, this plate, I've got its density varies across the plate. So what I'm interested in is how is the mass distributed in relation to the y-axis. So we take each little mass element, that's the rho xy dA, each little mass element, and work out how far it is away from the y-axis. That's the x value. We take the product, and that's the tendency that little mass element has to rotate about the y-axis. It's its mass times the distance from the y-axis. And we integrate over all of the plates, so all of those little mass elements and their distances from the y-axis, and that's the tendency the whole object has to rotate about the y-axis. And so that's what we call the moment about the y-axis. So you can see it, we call it the moment about the y-axis, m sub y, but we are multiplying the density function by x, because x is the distance our arbitrary point is, that we're looking at the mass element of. That's the distance from the y-axis. So let's have a look, not in the continuous case, not in the continuum, but in just the discrete case. So we'll simplify the problem a little bit. We've now got three masses. You can see they're labeled there, M1, M2, M3. And just for simplicity, I've made the mass of M1 to be 1, the mass of M2 to be 2, and the mass of M3 to be 3. And they're sized in that way. So what I'm interested in is, if I think of an object that's just made up of these three mass elements, if you want, you can think of there as being rods connecting all three of them. So we got these three mass elements and then a rod of negligible length that's connecting all three of them together. What is the tendency that this rod has to rotate about? And I'll hold it this way just so we don't get confused with some extra dimensions here. Try to line it up perfectly. What's the tendency this rod has to rotate about that center point, about the origin? So we've got some masses distributed on the right, a mass distributed on the left. What's the tendency this whole object has to rotate? Well, what we do is we look at the tendency that each mass has to rotate about the origin. So we got the mass M1, its mass is 1, and its distance from the origin is 2. So the tendency it has to rotate about the origin, what we call the first moment of that mass, is the product of its mass times its distance. So that would be 1 times 2, or the first moment of that mass is 2. That's the tendency it has to rotate around the origin. That's a measure of the tendency it has to rotate about the origin. What about M3, also on the right-hand side? Well, it's a mass 3 of distance 4. So 3 times 4 is 12, so the first moment of that mass is 12. That's a measure of the tendency it has to rotate about the origin, to cause this whole system to rotate about the origin. What about the mass on the other side? Well, its mass is 2, its distance is -4, so the product of m times its distance is -8, so that's the tendency that that mass has to rotate about the origin, or in other words, its first moment. And so what we do is we add up all of the first moments, and that gives us the measure of the whole system to rotate. 6 is the sum of the 3 moments, so the whole system, the tendency it has to rotate about the origin is 6. What does that mean? Well, what it means is, imagine I replace this whole system with just one mass, which has the same mass as all three of them added together. So I take this whole system and I just replace it with one point mass. So its mass would have to be the sum of the original 3 in order for it to be an equivalent sort of mass. And so that would be 1 plus 2 plus 3, or 6. So the mass would be 6. But now I want to place that mass somewhere so that it gives the same moment as this system, so that it has the same tendency to rotate about the origin. Well, the moment for this system we worked out, it was 6. So now I want to try to figure out, where do I place this mass? The mass is 6. I want to place that mass some distance from the origin. So let's say that distance is d. So I want 6 times d. That will be the moment of this new mass. I want that to equal to the moment of the whole system, which is also 6. So I want 6d to equal 6. So that means d has to be 1. So that means this whole system could get replaced with a single mass of 6 at position 1. And so there it is. That whole system of 3 masses has a tendency to cause rotation about the origin as equivalent to putting a single mass, 6, 1 unit away from the origin. And then we can play a little bit with this. I can change my mass variables. I can say, what happens if I make my first mass variable a bit bigger? Well, you can see it's causing a tendency to rotate. It's more likely that mass over there is causing this rotation to be sort of, if you want to think about it, in the clockwise direction. And so replacing with a single mass would be a mass that's a little bit further away to cause more tendency for the rotation. If I increase M2, then it sort of pulls it back. And then at some point I can make my M2 value big enough so that it perfectly balances. So that this 3 mass system perfectly balances at that center point, and that's really saying telling me that I could replace that system with a single mass of value, whatever the sum of the three masses is, right at the origin, because that would have no tendency to cause rotation about the origin. So that's what our first moments are. They're this tendency to cause rotation. So the second integral, we also have, again, 1 over mass times, and then an integral there. What that is giving us, it's the y center of mass, but the integral I've circled in purple is the moment about the x-axis, and that's denoted by m sub x equals the integral r y rho xy dA. So that's the moment about the x-axis. And the y center of mass for the object is given by 1 over m times this moment about the x-axis. Now I'll say a little bit more about where these formulas come from, because there's one more step, is to really say, okay, now we know the individual pieces. We know the x bar, the y bar, we know the m, that's the mass, and we know what each of those integrals represent. Those are the moments, the tendency to cause rotation about a given axis. But why do the formulas fit together in that way? Let's go back to our model here. Now I'm going to introduce that extra dimension. So I've got those three masses, and we can play with not only where they're distributed in terms of their x values, but we can also play with their y values a little bit. And I can move sort of the y values around as well. Now I have three masses that are making up my system, and I want to know two things. What is the tendency for them to cause rotation about the y-axis? What's the tendency for them to cause rotation about the x-axis? And if I was to take all three of those masses and replace them with a single mass, with the property that that single mass has the same tendency to rotate about the y-axis and the x-axis as the three-mass system. In other words, using our new terminology, I want this new mass to have the same x and y moments that the three-mass system does. Then I'll play a little bit more with this. Maybe I will drop the mass 2 down just to pull that green point away so that it looks a little bit more interesting. So there's where we would place the three-mass system if I wanted to replace it with a single mass with the same rotational tendencies or the same moments about the x and y axes. That's where I would place it. So I want the moment of the green mass about the x-axis to equal the moment of the blue masses about the x-axis. And similarly, I want the moment of the green mass about the y-axis to be the sum of the moments of the blue masses about the y-axis. So what does that mean? Well, that means the following. What is the center of mass? That would be the location of a single mass that represents the entire system. So that would be our replacing this whole lamina with a single point that has the mass of the whole lamina, m. And the distance I'm going to put it from the y-axis would be the x center of mass. And that has to be so that, because this is now the moment of that single mass about the y-axis, that should equal the moment of the three-mass system, and that's m sub y. Or in terms of the lamina, I've replaced the entire lamina with a point at a certain distance from the y-axis, and that moment, m times x bar, should equal the moment of the whole system. And the whole moment of the whole system is m sub y. And so that tells us that x bar should be 1 over m times m sub y. And that's our formula up above. And similarly, where would I place the whole mass? Or if I was to take the whole thing and replace it with a single point mass, where would I place that mass in terms of its distance from the x-axis so that it caused the same rotational tendency? I would place it at a spot where m times y bar is equal to the moment about the x-axis of the whole lamina. And so that means y bar is equal to 1 over m times m sub x. So that's where those formulas are coming from. They're just trying to capture the idea of this rotational tendency. And so that would be the balancing point. This x bar and y bar would be the balancing point of that lamina. All right, let's have a look at an example. We want to find the mass of the plane lamina that occupies the region bounded by, there is an error here. We want this to be y equal to 0, not x equal to 0. So if your notes don't have that corrected, you can correct it now. And y equals 4 minus x squared. So this region looks like this. Y equals 4 minus x squared, so it's this parabola opening down. And we want y equals 0 as our other boundary curve, so that's the x-axis. So this is our region that we're interested in. That's our lamina. We've got our density function also for that lamina. So the further you move up the lamina, up the vertical axes, the higher the density is. So if I want to sort of indicate that in my drawing here by these sort of these lines, I'm adding lines where the density is higher, and then the density sort of thins out as we go down. So it's higher density the further up you go. So there's more mass situated at the top in some sense per unit area. So let's find the mass of the region. So to find the mass, we just integrate the density function over the region. So the mass is given by the integral over that region, let's call it R, of our density function. Our density function in this case is given by the name delta. So delta xy dA. So what is that in this case? Now we're going to set up our integral. We're going to integrate, let's treat it as a vertically simple or a y first integral. So if I'm going to integrate y first, y is going to go from 0 up to 4 minus x squared, and then x is going to go from whatever these intersection points are down there. So that's when the parabola crosses the axis, so that's going to be negative 2 to 2. We are integrating the y function. We're doing a y first integral, so there's the integral we need to compute. Let's go ahead and do that. Negative 2 to 2. The integral with respect to y, that's 1/2 y squared from 0 to 4 minus x squared dx. And so that's 1/2 the integral from negative 2 to 2 of 4 minus x squared all squared dx. So these are polynomials, so not so bad. We just need to expand them out. So this would be a 16 minus 8x squared plus x to the 4th dx. And actually, it might be worthwhile sort of stopping here and just noticing that this is an even function. We are integrating an even function over a symmetric interval. So we could just integrate over half the interval and multiply by 2. So I'm going to use symmetry here. And I'll get rid of that half. And then I'll just integrate from 0 to 2 of 16 minus 8x squared plus x to the 4th dx. You don't have to make this observation, but it's nice because when I go to work out the integral, one of my endpoints is 0, and that's always nice to use when you work things out. So this becomes 16x minus 8/3 minus 8/3 x cubed plus 1/5 x to the 5th, 0 to 2. So this is where the benefit comes in because I don't have to worry about plugging 0 in. But when I plug 2 in, I get 32 minus 8 times 8 or 64/3 plus 2 to the 5, that's 32/5. And that works out to have a value of 256/15. And so now we've got the mass. Now we're interested in the center of mass of this lamina. So what's our center of mass? Well, here we could make some observations that will help us in calculating. So first of all, if I wanted to balance this thing, now I just want to imagine balancing it, say, across the y axes. Is it already balanced? the density function just depends on the y value. So it doesn't depend on the x value. So the density only changes as we move vertically up. So what that tells us is that the right-hand side and the left-hand side of this object are going to be symmetric with each other. They're the same. And so the y-axis is a balancing axis for this. It's going to balance perfectly along the y-axis. And so that means our x center of mass should be 0. And that's just by symmetry. You can go ahead and you could compute the integral if you wanted and see that you get 0, but we could also just make this observation. What about the y center of mass? The y center of mass is going to be 1 over the mass times the integral over the region of y rho xy dx dy. And we know the mass is 256 over 15, so I could write that as 15 over 256. We are integrating over the same region, so we can look above at our integral for the mass and just rewrite out the limits of integration. The only difference is we have an extra y in our integrand. So in this case it's y times the density function, or y times y, which is y squared dx dy. So that's the integral we want to compute. And again, now at this point this is just an exercise in integration. We want to integrate polynomial, plug things in, integrate again. Nothing exciting really goes on here. These are integrals that you've done a ton of times before, so maybe I'll erase that first equal sign and just say this eventually boils down to a value of 16/7, which is approximately 2.29, so on. So that means in our picture up above we have a value of 4 where that vertex of the parabola is. Where's our center of mass? It's going to occur on the y-axis because x bar is equal to 0, and y bar is 2.29, so it's a little bit more than halfway. So it's somewhere around here is our center of mass. That's x bar, y bar, which is 0, and I'll just write the approximate value in, 2.29. It's a little bit more than halfway up. So the density really made the difference, because in terms of just area, there's a lot more area below y equals 2 than there is above. But because the density depended on the position, it was a higher density lamina the further up you go, so that density pulls the center of mass upwards. Alright, so that's it for this example involving the center of mass. We will come back to these kinds of integrals for physics problems. We've just looked at the first moment essentially, and then the center of mass. We'll come back to this idea of a second moment, or a moment of inertia. But before we do that, we'll venture off into an application of double integrals into finding volumes of solids.